But here's the rub, right? This is what we're really interested in, not finding the area underneath the rectangle. Okay? But how do we approximate the area between this curve, f of x equals x squared and 3, and the x-axis from x equals 1 to x equals 9? Folks, there are times where I will maybe forget to approximate the area between this curve and the x-axis. But if I say find the area beneath the curve, that's what I'm talking about. Okay? So notice here, and this is extremely important for these next couple of units, or excuse me, next couple of sections. Pay attention between when you're asked to approximate the area versus find the area. Okay, if I'm asking you to find the area, there must be some way to find the exact answer. If I'm asking you to approximate the area, you're going to use one of the approximation techniques we're going to learn in this section. Okay, so do pay attention to that. Okay, and we're going to approximate the area using the left endpoint method for 4 rectangles. Okay. All right. Folks, I know some of you have done this before. Some of you, this is brand new. Okay. I wish everyone came into this class with this being brand new. Okay, because it's an interesting thing to do the first time. All right. We're trying to find this area right here, and I will actually shade this. You don't need to. This is just for illustrative purposes. We're being asked to come up with a guess of what I've shaded in red right here. Okay, I don't recommend doing this because we're about to. I can do this because I've got these multiple colors and stuff. So maybe if you do it oh so lightly. Okay. All right. We want to approximate this area underneath the curve here between x equals 1 and x equals 9. Okay? We are going to approximate this by breaking it up into segments and then matching a rectangle to each one of those segments. Okay? Integral calculus starts off by using rectangles to approximate area underneath the curve. Okay? That's how this starts out. So we want to use, we're told in this problem to use how many rectangles? 4. Okay, I want to go ahead and let's just right away, let's start introducing some notation here. Okay, so we're going to call the width of each rectangle in fact, let me call that the base of each rectangle. The base of each rectangle, we're going to call it delta x. Okay, the choice of that notation isn't clear yet. Okay, but we'll use delta x to be the base of each rectangle. Okay, and delta x is equal to b minus a over n, where b is the rightmost endpoint, a is the leftmost endpoint, and n is the number of rectangles. Okay, so in this problem, what was the rightmost endpoint? 9 minus the leftmost endpoint, which is 1. All divided by the number of rectangles we wanted, which is 4. So this gives us 8 divided by 4, which is 2. Okay? So the width of each one of these is going to be 2. Okay? So let's go ahead and start. Let me be a little more careful there. Let's go ahead and start. This will be my first rectangle between here and here. Oops, that's not true. Between 1 and 3, right? That'll be my first rectangle. Then my next rectangle will be something between 3 and 5, and then I'll do 5 and 7, and then 7 and 9. Does everyone see that? This gives me, you can see how I've tried to draw these larger dashes here. That gives me how many regions? 4. Okay, let's start stressing this right away though. I've got 4 regions. How many tick marks have I made? 5. This is important. Okay. If I want to break something up into 4 segments, I need how many boundary markers? 5 boundary markers. Okay. So if you want to think, I think this is helpful. If you wanted to make 4 sections of fence, how many fence posts do you need? 5. Okay. Some of you will mess up on that. Don't worry. I've been to the lumberyard more than once on one day as well. Okay? So you need 1 more post than you do sections of fence. Okay? So keep that in mind. All right, so right here for this first region, I want to construct a rectangle that somehow matches the area of the curve. Okay? Well, what I'm going to do is I'm going to go up until the left endpoint intersects the curve. That will be my first rectangle, and I'll shade that green here. There's my first rectangle that I'm using to approximate the area beneath the curve. Okay? And I'll draw the second one in a minute, but here I just want to emphasize what we're doing here. So let me draw I'm going to jump out of order. Normally you wouldn't do this. I'm going to draw this third rectangle here, and please don't write it down just yet. Okay? So one way I could construct this third rectangle is like this. That's one way I could construct this third rectangle. What did I do here? Well, I drew a rectangle that rose up until the right side of it intersected the curve. That's called the right endpoint method. Okay? Well, that's not what we're being asked to do in this problem. Okay? There are many other ways I could do this. I could go up until the midpoint of the rectangle intersects the curve, and then construct the rectangle like this, and that would be called my midpoint method. Okay? But we're not asked to use either one of those. By the way, there doesn't actually have to be a rhyme or reason. I could pick some random x value in here, call it x star, and it's inside the third interval, and I could go up to where this point intersects the curve, and that's where I make my rectangle. Again, you don't need to write that down. We're not going to do this yet. But I just want to show you that there are different methods for doing this. Okay? All right, but here we're specifically tasked with using the left endpoint method. So here's my second rectangle.
You don't go above that curve at all, right? To hit up the next plane.
Well, if you remember when I did the right endpoint method, I did.
I just meant for the left endpoint.
So here's how I want you to think about it. In this case, no, you're exactly right. In this case, I'm never rising above the curve.
Okay.
But that's actually specific to the curve itself that we're dealing with.
Okay.
And I'll have you make a hypothesis on that going forward. We'll keep thinking about that question because it's a really good question. And yeah, you're right. In this case, I will never make a rectangle that goes above the curve, but that is not because of the method that I'm using per se. It has to do with the structure of the curve itself. Okay? All right? And so then for this fourth one, we go up till the left endpoint intersects the curve. And there it is. Okay? Pretty ugly. I think you can follow your way through it. Okay. So, any questions on this? So if we want to approximate the area beneath the curve, all I need to do is take this base times this height, and add to it this base times this height, add to it this base times this height, and the last rectangle as well. We're going to be summing up the areas of a bunch of rectangles. That's what the second half of calculus is about. Summing up the area of a bunch of rectangles. Okay? So, one thing I want to do right away is you will not always be able to quickly graph the function that you're working with. Okay? So I think that you should always draw yourself a picture for these problems. It doesn't have to be an accurate picture. So let me show you what I would do if I were tackling this problem. Okay? If I didn't have this graph sitting right here, what I would do is I would go ahead and just give myself some arbitrary function that looks like this. Okay? It's usually a good idea. In fact, I'm going to change that. It's arbitrary, but I like to have it be kind of steadily increasing or steadily decreasing, just so my rectangles don't overlap in weird ways that are hard to look at. Okay? Then I go ahead and put my left endpoint, which was 1. I put my right endpoint, which was 9. Then I use my delta x to construct all the other intervals. Let's see here. Delta x is 2, so 1 plus 2 gives me 3. 3 plus 2 gives me 5. 5 plus 2 gives me 7. You see how I'm basically getting the same picture, okay, building it from scratch. And I'm not actually concerned with what the function actually looks like, but this is the critical part. Okay? I'm now going to draw the rectangles, and even though I don't care about what this graph looks like, I'm going to use the correct method when I draw these rectangles. So here we go. We're going to go up to where the left side of this first region intersects the curve. That's our first rectangle. Then we go up to where the left side of this region intersects the curve. And we do that for all of these. Okay? So for the rest of this problem, I'm actually going to look at, you can look at this picture. I'm going to look at this picture to finish out the rest of this problem because that's really what you'll be doing on your own. Okay? Here we have the actual graph, but generally we don't have that in front of us. Okay? All right. So not a lot of room down here at the bottom, but we'll get it in. All right. So we're going to say that the area underneath the curve can be approximated using the left endpoint method. I'm going to put an L there. For the left endpoint method, how many rectangles do I have? 4. So I'm going to put a subscript 4 there. Okay? That's my choice of notation. Some books use it, some books don't. Okay? So now pay attention to when I use the equal sign versus the approximate sign. Okay? We're saying that the area underneath the curve is approximated using this method. That makes sense, right? We're not going to get the exact area underneath the curve using these rectangles. Okay? But how would we do this left endpoint method? Well, what we're going to do is we're going to take the functional value evaluated somewhere in this first interval. Well, because I'm using, here's my first interval, right? So I could pick, for this first interval, I could pick any number between 1 and 3 to give me the height. But because I'm using the left endpoint method, what value am I going to plug into the function here to get the height of this first rectangle? 1. So I'm going to take f of 1 times delta x plus, then I'm going to take f of what? Yeah, f of 3 delta x. Notice I can get all of this from this inaccurate picture on the far right here. From this inaccurate picture, I can get all of this information. Okay? Plus f of what? 5 delta x plus f of 7 delta x. Folks, breaks my heart if you then write f of 9 delta x. Why is this wrong? At just the most superficial level, why is this wrong?
Because you're evaluating that.
Well, I mean, here's a 9.
But it's left.
I think that all of your responses for as to why that's wrong are just fine. Let me give you just a much more obvious one. We're adding up how many rectangles here? 4. How many rectangles? I've got a base times, a height times a base, a height times a base, a height times a base, a height times a base. There are the 4 rectangles that I was asked to add up. Okay? So I do not want this 5th rectangle here. Okay? Great. So if you plug 1 into this function, let's see here. Well, it's 1 squared plus 3, so I think we get 4 times 2, right? Then adding, well, we plug 3 into the function. Let's see, I think we get 12 times 2 plus 28 times 2 plus 52 times 2. Everyone see how we got those? How do I get that last 52? So we plug the functional, we plug 7 into the function, right? Okay. So what we did here was we said, hey, this height, this is the ordered pair right here. This is the ordered pair 7, 52. And we took that height value on the function to give us the height of this the last green rectangle. Okay? If we add up all of those, we get 192. Okay? Let's just be kind of cute here. Let's put units squared. Okay? Just to remind ourselves that we have just computed the approximate area underneath this curve. Any questions on that? Yeah, Maria.
Would the area be closer if we did a right?
Great question.
Or left endpoint?
Yeah, so we're going to do the right endpoint method on this in just a second. The question of which one's closer is a really interesting question that we're not going to get into in this class because neither one of these are going to be close enough for what we want. If you're really interested after we get going through this, ask yourself something about the concavity of the graph, and that might help you see better which one's a better approximation. Yes?
Why did we choose delta x? Did we choose it to be that, or just how did
Well, so we didn't choose delta x to be
Yeah.
2 at face value,
delta x to be? Yeah.
but we did say we needed to use 4 rectangles.
So, okay, but if we do it with like less rectangles, wouldn't it be closer to?
Yeah, we're supposed to be approximating the area underneath the curve, right? We used 4 rectangles. What if we used 6? What if we used 8? What if we used 100? 1,000, 10,000, oh, I can see where this is going, right? I can see where this is going. We want to let the number of rectangles increase arbitrarily, right? That's where we're going with this. Okay? We got a lot of notation to do before we can do that.